Okay, so we've talked a lot about the division algorithm and division in general, greatest common divisors. Uh, Really, we've completely been leading up to um, the Euclid's algorithm, or the Euclidean algorithm, as it's called. And the Euclidean algorithm is a method for finding a really awesome method for finding the greatest common divisor of two numbers. So let's take an example here. Um, all right, so the first exam, so well, I'm going to type this time because the writing has been a little tough, and typing actually turns out to not be so hard for this particular example. So let's try and find the greatest common divisor of, say, 120 and 45. Okay, so one method for doing this would be to list the divisors. So 120, we have 1 and 120. Then we have 2 and 60. And then 3 also goes into that. And 3 goes in, what is that, 40 times. Then we have 4 goes in 30 times. And then 5, let's see, 5 goes in how many times? 24 times. And then 6 goes in 20 times. 7 does not go in, finally. 8, does 8 go in? Let's see here. Yes, we have 8. And then 8 goes in 1, subtract 40, 15 times. All right, does 9 go in? No. And does 10 go in? Yes, 10 goes in 12 times. Oops, 12 times. And does 11 go in? Nope, and we are done. All right, so there we have the divisors of 120. Let's try 45, a little easier. We've got 1 and 45. We've got 2, no, 3, yes. 3 goes in 15 times. And then how about 4? Nope. 5. Yes, 5 goes in 9 times. 6 does not go in because 2 doesn't go in. 7 does not go in just because it doesn't. 8 doesn't go in. And then we're back to 9. So we're done. All right. Great. So we look at this list and we see here we've got 15 and we've got 15. So the greatest common divisor is 15. Okay. But that's sort of the brute force we have to do, right? Let's just take a look at another example here. What is the, well, yeah, so let's do this again. We want to do the GCD of 120 and 45, okay? But, well, yeah, we've already done it. What's 120 minus 45? Well, 120 minus 45 is 75, right? Okay. What is the GCD of 120, I'm sorry, of 75 and 45? Not 74, 75 and 45. 75 and 45, well, if you think about it, that actually is also 15. Interesting. What if I do the GCD? Well, let's say, what's 75 minus 45? 75 minus 45 is 30. What's the GCD of 45 and 30? Well, that actually turns out to be 15 also. Oh, I never filled the wrong answer up here. Let's do that. So the GCD up here is 15. GCD of 45 and 30 is 15. What about 45 minus 30? What's 45 minus 30? Well, that's 15. Okay. What's the GCD of 30 and 15? Well, it's 15. And what about 30 minus 15? What is that? That is 15. And what is the GCD of 15 and 15? Well, that's 15. All right, so we see I did a whole lot here, right? And in each case, the GCD didn't change. So let's take a little bit closer look at this, right? Okay. So if we go to my mouse, all right, we started off with the GCD of 120 and 45, and the goal was to find that. We found it was 15. Okay, but I said just for fun. No, not just for fun. I knew where this was going, but just for fun, what's the difference between 120 and 45? And the answer it's 75. And it turns out that the GCD of 75 and 45, the GCD of that difference is actually 15. Now, why did I do that? Well, I'll tell you, the bigger the number, the more factors it has potentially, or the more divisors it has potentially. So the harder it is to calculate the GCD. So I thought, well, if we subtract the two, it makes the number smaller. 75 is definitely smaller than 120, so maybe it's an easier calculation to do. But if we can do it once, why don't we do it again, right? And if we can do it again, why don't we do it again? And if we can do it again, why don't we do it again until we get down to something like this, which is 100% obvious, right? So this essentially is Euclid's algorithm. And what I did here was I subtracted. Now you may think to yourself, okay, great, you did a whole bunch of subtraction, but how do you know that the GCD stays the same at each step along the way? Well, we're going to prove it in a little bit, but before we prove it, let's do one more example. Okay, so this was our example 1. Example number 1, all right? And we first set out to find the GCD, and we found the GCD of 15, but then we did this sort of reduction, right, where we made the numbers smaller at each step along the way, and we saw that the GCD actually didn't change. So we already knew the answer, so there was really no point in doing this. But what if we had a bigger problem? What if we wanted to, say, do the GCD of 1989 and 867? Okay. Well, we can do that if we do that in a similar way. Now, full disclosure, I stole this example from Wikipedia. If you look up the Euclidean algorithm on Wikipedia, you'll find a really nice page. And this example is one of them. Some of the stuff on the page is a little bit, I don't know. It's not very clear. So what we're going to do is hopefully a little bit more clear than that. But if you want to go reference that, go nuts. Anyway, so the method that we did was we took the two numbers and we subtracted them. And if you notice, I always put the smaller one second and the bigger one first, and I always subtracted the smaller one from the bigger one. So let's do that. Let's take 1989 minus 867, and when I do that, I get, a little quick mental math, I get 1122. Okay, so theoretically, if what we did before was correct, this should be the same as 1122 with the GCD of 1122 and 867. Okay, great. So again, still too big, so let's make it smaller. We make it smaller by subtracting the smaller one from the bigger one again. And in this case, when you subtract them, you get, what do you get? You get 255. 255. Okay, so we subtract those two, get 255. Let's do it one more time. Now we've got the GCD. Now notice 867 is now bigger than 255, so I'm going to put 867 first. So I go 867, 255. Now the GCD of 867, 255 is the same as the GCD of 255, 867, so it doesn't matter. I'm perfectly free to do that. Okay, so again, I don't know what that is off the top of my head, so let's just do it again. We got 867 minus 255 is equal to, what is it? It's 612. All right, so now we do GCD Again, 612 is the bigger one, so I put that one first. Still don't know what that one is off the top of my head, so I'm going to subtract them. 612 minus 255 is 357. Okay, GCD of 357 and 255. You know, still not knowing that one, so let's just do it again. 357 minus 255 is 102. Okay, we're getting there, but I still don't know the GCD off the top of my head. But I do know, you know, some factors of 102, for example, so that's always nice. Okay, so now 255 is finally the bigger one, so it goes first. Again, we'll subtract 102. 255 minus 102 is, what is it? It is 153. Sorry. Got a little distracted there for a second. So 153 and 102 is also what we're looking for. Okay, take 153 minus 153 is divisible by 3. Is that helpful? Maybe. 102 is divisible by 3. Maybe 3 is the GCD. 103 minus 153 minus 102 is 51. GCD of 102 and 51. Let's see here. Wait a second. 51 goes into both of those. Well, that means that my answer should be 51, perhaps, but let's just keep going because we can. Let's say we didn't notice the 51 goes into both of those. We go 102 minus 51 is equal to 51, and now we get to the GCD. What's the GCD of 51? 51, the answer is 51. Yay! Okay, so the final question is, does 51 go into 1989? Right? Well, 1989 happens to be equal to 51 times, what is it? It's 39, sorry. If you check that, let's see. 50 times 39 is 150 plus 45 is 195. So 1,950, and then 1 times 39 is 39, so I add 39 to that, and I get 1989. Perfect. And also, we have that 867 is equal to 51 times, let's see, that goes in there once, 35, it's 357, you know what, I'm just going to get some help. 867 divided by 51 is 17. Awesome. Okay, great. So these, we got that. Now, if you were to list them all, you would see that 51 is the greatest. Not only is it a divisor of both of them, it is the greatest common divisor.